Someone unmute Tobi for him.
Oh, sorry, I was muted. So the slide here, Christoph, thanks for asking about this. This slide, which I can't show properly because it has my video in it, and I don't want to delete my video. I'll just delete my video from the slide. And now I can play this slide. So you're asking about this slide, Christoph? Christoph, are you there?
Yes, okay, I've unmuted myself again. Yes, I was asking about that, but right now I'm just seeing the, okay, so you're bringing the slide up one by one. Yeah.
Okay, so I'm just asking, so in the original silicon retina, which you see the mouse movement, you had an array of pixels. This is really frustrating. It's just really bad. Sorry, guys. I need to find the right slide here. This must be quite frustrating for you. I'll just show the whole slide. The original silicon retinas that were first developed.
There is an
echo.
Christoph, I think you need to hear.
Yeah, mute yourself, Christoph, please. You have terrible feedback. In the original, very first silicon retinas and also neuromorphic chips, you had an array of pixels, which is indicated by the mouse here, the blue array. And on two edges, you had this arbiter that would arbitrate between the rows and columns, the row and column requests. And then first you would send out the row address as that blue square. I can't indicate with my mouse here for some reason. You would send out with that blue square, and then you would send out the column address one by one. So every time you sent out an event, you had to send out the row address and then the column address. And that was really slow. And so you only achieved about 1 mega event per second. From our DVS 128, which is still quite a practical camera, we only got about 1 million events per second peak. In practice, less than that. Now then, Kobena came along and developed the AER word serial algorithm or architecture, which he published in some really nice papers around 2014. But now you replace the column arbiter, the blue-green column arbiter that you see on the bottom left there, you replace it by a circuit that would basically store the active columns and then read them out one by one. You would read the row address once, and then you would read for each active column, you'd read out one word of the column address. And then people said, you know, that actually got a lot faster. That got up to about, in current Davis cameras, that get us up to about 10 million events per second, up to 50 million events per second if you just tie the handshake, you know, signals to the closed loop, but it's really limited by USB bandwidth because you're still sending a lot of data per event, like 32 bits of data per event to the computer. And then people at Samsung first, and then later Prophecy, developed the so-called group vector, and then even later frame-based readout. So it's going back to frames, where now they still all use an arbiter, as far as I can tell, for deciding which row of the array has events. All right, but once they know which row has some events, now that they gather the active pixels into groups. And so, for example, this group of 3 pixels, I don't know if you see it here, this group of 3 pixels is collected into one word. And so each event in that word only takes a couple of bits of information to send out. So you can basically compress the active pixels in those groups of stuff into much smaller data. And so they can get much higher bandwidth. The actual schemes are quite complicated. And you know, they apply some compression and stuff like that. But basically what they've done is first Samsung went to 300 mega events per second. And then Prophecy and Sony went to acclaimed 1 giga event per second peak. But basically by just reducing the number of bits per event in a smart way. And then also people like Samsung, they do stuff like they now, and also in Sightness, what they do is they say, look, we don't really care about events. What we care about are sparse frames. As long as the frame rate is high enough, like 1 kilohertz, 2 kilohertz, that captures all the dynamics you might care about. And so they'll actually read out sparsified frames of data. And they can do that using like a mobile industry processor interface. This MIPI is a standard kind of electronic interface between a camera and an application processor on a smartphone. And that makes it a lot more compatible. You know, that asynchronous data is really weird to deal with. And so to make it compatible with something like MIPI, you have to really read out frames. And so Samsung and probably Prophecy, Sony integrate some kind of MIPI intellectual property block on their chips that allows the chip to just read out these MIPI frames. I hope that helps. But having said all this, the problem with this whole approach of increasing the bandwidth is kind of contrary to the whole idea that you should really have sparse output. you shouldn't need this high bandwidth. Right? You should really produce a very sparse output that is occasionally high bandwidth. I hope that's helpful.
Yeah, that's somewhat helpful. Is it now without the feedback?
Yep.
Feedback?
Okay.
Feedback?
Yeah. Follow-up question. I think you're doing the same trick later on in the processing, which I know nothing about, but you seem to have, as you're trying to group events as they come in, as you have very active frames and not so active frames.
Oh yeah, let's talk about that. Okay, this is a very important topic which comes up over and over again when people try to do things with machine learning with this DVS output.
Yep, that's the slide.
Is that me?
Christoph, you need to get hooked.
Yeah, I think there's some video playing in the background. Okay, so interesting thing. How can you get the data out of one of these cameras and drive a neural network with it? Okay, obvious thing is you could, I'm just gonna not play the slide. Obvious thing is you can just take the individual events and drive them into an SNN. Problem is, you know, SNNs are very obscure objects. It's not so clear that they're always needed. Just for pure efficiency, just like an all computing system, often pays to buffer stuff into chunks and then do stuff with it. And so, of course, when we started driving a neural network with DVS, we would collect frames of signed or unsigned DVS events, like you see in all these pictures that I showed in the very beginning of the tutorial where, you know, like this one here. Basically, this is a histogram of some events over some time frame where gray means no events, white means there were on events, and black means there were off events. So say this is like a 1 millisecond frame. It means there were some off events here, on events here, and everywhere here there were no events. And so you consider this just a picture, kind of a granular picture that you can drive your CNN with. Now this is actually really cool input to drive into a CNN if you can exploit sparsity, activation sparsity in your CNN, because all these pixels here are 0. And since these pixels are 0, if the hardware exploits this, GPUs don't, but if the hardware did exploit it, then you basically would do no operations with those pixels right away. So you right away save tons of operations with a sparse input, like in a surveillance scene, you know, or tracking object scene. Of course, if the camera is moving and there's lots of texture, it's not sparse anymore. But, you know, basically you can exploit the sparsity right away if the hardware supports it, which it will soon. And so, like our hardware accelerators exploit that activation sparsity, or, you know, some of the ones that were talked about today. But that's only one way to make a picture, is to take these constant time frames. So you take delta t. The other obvious way that existed in JR, our software ideas, you know, since the very beginning, is to take constant count frames. And incidentally, these methods are compared in this paper in IEEE Signal Processing magazine. It's quite a nice paper where we did some new experiments comparing different methods of sampling event-based data. I'm not even going to talk about timestamp image and surface of active events and stuff like that. That's only if you really care about precise event timing. But if you don't care about that, you can just make frames, which are perfectly fine as long as the sample rate is sufficient. And now instead of making constant time, you make constant event count. You just have like 1,000 events per frame. And that means that the faster you move something that's moving in, the faster you get those 1,000 events and the higher the frame rate. But if things start moving really slowly, of course, the frame rate slows down. So that's really cool, easy approach, you know, that makes an adaptive sample rate. And you still get the advantage of sparse frames, right? The frames are mostly sparse. But the problem with this approach is what? What do you think the problem is? Well, it's said right now, a busy scene or large objects makes a much higher frame rate than a small object, even if moving at the same speed. So like if I hold my hand really close to the camera and move it, I'll get 1,000 events much quicker than I would if I took my hand back here and moved it. You know, that's really not a good idea, right? It means that my hand will get really blurry.
Tobi,
it means that my hand will get really blurry.
Tobi, the latency of your video is a problem right now. Yes, Tobi, the latency of your video is a problem right now.
Of my personal video? Maybe for you it's a problem.
I'm being facetious.
Yeah, it looks, I don't see a problem. Yeah.
You don't see me? Look at my video of my hand moving.
Yeah, no problem with latency here in California.
Yeah, it's working over here as well.
No problem with you too.
Yeah, Christoph, it's your laptop, man. You need to buy some new horsepower, I think. You were complaining about your old laptop, right? Your old laptop. Your codec is not keeping up.
Tobi, yes.
Your codec is not keeping up.
Yes, that's the one thing. The other thing is that I am using your video to illustrate the problem of latency, which is the problem with the constant count, I assume.
You mean that it takes a while to collect those events? Yeah, that's true. If you care about really, really quick latency, you have to make sure that you terminate the frame, quicker, right? And that's why all the cameras include this early packet timer that makes sure that the camera, this camera, in the logic of the camera, there is some called early packet timer that when it collects a buffer of events, it makes sure that the packet is sent to the computer at least in a millisecond, at most a millisecond. It can get sent many times per millisecond, but every millisecond it sends whatever data it has. You understand? So that makes sure that the biggest latency coming from the camera to the computer is a millisecond. So you have to do stuff like that. It's not that difficult. Anyway, I wanted to get to the point that other people are thinking about other representation. I won't talk more about this, but there's some cool things you can do that are really quite cheap to get around this problem of size in the image. Like this area count is one method, which I think is quite practical.
And one thing worth kind of pointing out is that, in the biological systems, we don't have this concept of frames. And so just by kind of focusing on how do we create frames from a DVS, kind of right off the bat takes us out of a neuromorphic regime,
but
in some ways.
I just really hate that viewpoint. I hate that viewpoint, Guido. I have to express very strongly that you shouldn't be too religious about the biology. If you think about the biology and the biological computation, that's fine. If you're a computational neuroscience and you want to understand how this hardware does it, that's great. No. But if you want to understand how to do it best, don't get religious about your approach. That's what held back the whole field of neuromorphic engineering for a long time, this religious attitude.
Make a non-religious argument in this direction. So I think that the thing that makes something...
I agree with you.
Yeah, Terry, please speak up.
Okay, I agree with you, and it really depends on what materials you have and what's the best use of the material. For example, in the brain, there's a lot of wires. You got a million ganglion cells that project into the optic nerve, but you don't have a million wires right with your chips. So,
but you have 10 million times the mobility.
Yeah,
right?
so it makes a lot of sense to try to use the digital part, and there are a lot of ways of doing it that have different strengths and weaknesses. But the fact is, though, that you don't have to be religious. There's no reason to be religious with the practical side, as long as you have the same outcome, right?
So I made the mistake of saying the part that makes Toby angry before the part that I think he will agree with. So I wasn't trying to be contentious here. One thing I would say is that the lesson that I pull from biology is that there's never a single solution for anything. It's always especially tailored to a really unique situation, and that I don't believe that there is an appropriate one-size-suits-all for neuromorphic vision as well. And I think a lot of the time there's really interesting stuff that can be pulled out of just the temporal information at a really high frequency as well. So sometimes this implies treating the event stream as a one-dimensional signal and pulling out power in that signal at different frequencies and processing these things in ways that never even make it to the reconstruction of an image. I think at other times, obviously, we do need to reconstruct something of the world around us in multiple dimensions, maybe not even just 2D, but maybe also 3-dimensional. And so I think that there's a lot of room for growth besides frames to, in terms of treating these things as one-dimensional signals, as 3-dimensional representations of the world. But like the temporal component is the really rich and wonderful and truly neuromorphic aspect of this.
But that fascinated me for a long, long time, and I worked a long time on handcrafting feature extractors that would extract orientation, optical flow, and many other people, like Riyadh did some really nice work in that domain, many other people. But I mean, for certain things like where the fine timing does matter, really does matter, like flow, and you want to detect flow over many scales of speed, at low cost, then the timestamps may matter, but for other stuff, it may not matter. I'm just saying, don't think that the timestamp image is good for everything.
Toby.
In practice, sorry, Andreas, I had to finish. In practice, the integrated event count image is better representation than this timestamp image for many real problems that we've done.
But Tobi, that's kind of a viewpoint which, and I want also to comment.
It's not a viewpoint, it's an experimental fact, Andreas.
Always
we measured it. We compared timestamp image with time surface with just integrated event counts, and just making the picture works just better.
Someone will come and tell you, I want to do faster than what you do, okay? And to do faster, you really need to timestamp in as fine resolution as you can. There is applications.
Some application, that's true. That's true. Who cares?
And I'm gonna say, let's push the limit to something where you can solve a problem beyond what humans are doing. Anyway, I want also to go back to Terry. Terry, actually there is really kind of a change in system on chip design recently. People are going back to wires. It doesn't pay off to actually route packets between the processors on a chip. It's not efficient, it's not energy efficient, because now the wires have become so small, it's much easier, and we do it not just for processors. We can run 500 wires north, 5 south, 5 west, 5 east, both directions, 1,000 wires between 2 pixels, you know, to get a high-speed camera or a high-speed processor. So we are back to the wires. So the wires is really, at the end of the day, what matters.
And Andreas, you're talking here about 3D integration, right?
I'm talking about just in 2D, in 14 nanometers.
Yeah, but Andreas, you have to lay down as many wires as you would need to have in the, in your network. And biology is not like that, right?
Well, biology
will grow with the wires
we have a lot of wires.
But it grows the wires where it needs to, and you'll take it away where it doesn't want to. And biology is so much
I
more.
don't know.
It's alive.
Anyway, Andreas, there's one thing that biology is definitely worse at, which is multiplexing. And silicon is worse. Silicon is frozen, and it's bad at, it doesn't have all the power of this molecular computation, but silicon does have the ability to multiplex signals because of the high mobility of electrons. Anyway, this is all getting off this tutorial. People are supposed to be able to ask me questions.
Try to build an imager, a centimeter imager, and try to multiplex column or rows, and come and tell me how well it's going to work.
No, I mean, I'm just telling you, that's why people can build these 20 megapixel image sensors and still run them at 1 kilohertz, because the electrons are so fast.
I know, but if you want them to run at 100,000 frames per second, you cannot do that.
Yeah, but that's a specialized thing. I mean, I'm just saying the electrons are very fast, so it pushes you in a different direction.
I'd just make a related point that,
anyway,
it was often said in the neuromorphic community that time represents itself, right?
Yeah.
But in the case of event-based sensors, this whole idea that you transmit the XY polarity and the timestamp has become so ingrained that we don't even notice it, right? But very few people have actually exploited this idea that you don't need to transmit the timestamp because you do stuff in real time. I think the only person really—
That's not true at all, Sam. That was the roots. That was the roots of the whole thing. And the original, you don't even know in the beginning, in the Caviar project where the DBS came from, there was no timestamp. Everything was just representing itself, and all the whole history.
That's my point, right? We've gotten so far away from that, right? Now we always transmit the timestamp, right? We always allow that to be processed in batch downstream, but actually
for efficiency and flexibility. Yeah.
Yeah. But
what's
the point? Yeah, that's the point. We've just moved away from this vision.
On a big imager, that will not work just to transmit the XY. You won't be able to do that. You need to really timestamp. You need to code, as Tobi pointed out earlier, what Samsung is doing and others.
So I have a question. Is it possible to do more than one protocol on the same? Why not have two? That could be used for different purposes. One could be timestamped, and one could be direct events as going across.
Yes, for sure. You can just disable that. You should be able to just disable the timestamps. In fact, in your Conrad's lovely embedded microcontroller applications of DBS, he doesn't even bother timestamping the events in his microcontroller code, even though he's processing the events procedurally, often in frames, well, actually, he doesn't really use front, but like, for example, in the pencil balancing robot and stuff like that, he doesn't bother with the timestamp. Time represents itself, even though it's kind of chunked by the microcontroller.
Yeah.
He doesn't bother transmitting the timestamp because it means that, you know, he's using up precious microcontroller clock cycles dealing with those timestamps. It's kind of an obvious point, right? Since the thing is always processing the events as they come anyway, so why bother dealing with the timestamps?
Yeah,
That's what makes these things. That's what makes these things so appealing, is that if you can design your processing loop to the specific application, you know, kind of the same way you get.
Or the hardware.
Yeah, exactly.
You know, you design dedicated digital hardware, like our student Min Lu is doing with his optical flow, and Garrick did this beautiful FPGA optical flow stuff that was rather simple optical flow, but it was all designed like hardware logic circuits that computed the optical flow based on simple, I think it was gradient-based method. And now our student Min is doing that for patch-based, for block-based optical flow and extracting key points and stuff. But it's all just hardware logic circuits that directly process the events as they come.
Yep.
Maybe it's chunked, you know, into memory buffers and stuff like that for efficiency, but it's still processing in hardware logic. I mean, it's not the old neuromorphic mixed signal stuff. But
so Tobi, I can tell you, so we're doing a lot with these sensors these days, and I think there's probably going to be a burst of interesting publications, you know, over the next year or two.
I mean,
things are getting into people's hands.
So nobody has any question about these stack sensors?
I've got a question. This is a question, not just a comment. So one of the things that we find ourselves doing quite a lot at MITRE is helping various government parties like try and wrap their mind around the concept of what does it mean to use this as an imager as opposed to, you know, frame-based sensor, and what can you do differently with it. And one of the recurring challenges that people come up against not only you know, relates to the downstream processing and, you know, how do we replicate the visual cortex, but like more to the operation of the sensor itself, the setting of the biases on these things, and like the configuration of the sensor under different environments can be really challenging. So do you have words of wisdom for people who are getting started with the hardware, have a unique problem in mind, but don't know how to configure the sensor?
I definitely have. I have some comments about that. So,
Guido.
that's a good question. Thank you for that question. It's something that hasn't really hardly been addressed at all in this field. I don't know why. It's because it's kind of part of the infrastructure and people don't consider it particularly interesting to work on stuff like parameter tuning. But I'll just show the slide here just as a basis for discussion. So, you know, in one of these pixels, I won't explain all the pixel circuit, but in this pixel circuit, you have certain bias currents, like this IPR, ISF, this ID, I on, I off, and this I refractory period. All these things determine the bandwidth, the event contrast threshold, and the refractory period between events. And typically users will just fix these values. Because of the pixel design, the functional behavior of the sensor doesn't change much with temperature. It's quite insensitive to temperature, but it's just fixed to a particular value. Now, what you don't understand, because you're not an image sensor designer, is that the fixing of the parameters of an image sensor initially was just like these neuromorphic chips. People had to fiddle around with the biases. If people remember the days of tube cameras, they had these very complex, like 15 different potentiometers that had to be carefully adjusted to control the biasing of these tube video cameras. In the same early CMOS cameras, they had lots of complex biases. Now, by many, many years of hard work, all those parameters have been hidden from the user, and now the thing kind of adjusts itself so that it works. Perfect example is automatic exposure control. Mm-hmm. The thing that it controls how long the frame is exposed for. It still doesn't work perfectly because, of course, it sometimes over and under exposes it, but those algorithms which control the exposure duration are actually quite sophisticated algorithms. They're not trivial feedback control algorithms. And these kind of algorithms that adjust automatically these bandwidth of the photoreceptor, the event threshold, and the refractory period do not exist yet for these event cameras. So I played around with some algorithms that would adjust these things, but for sure it hasn't been addressed yet, as far as I can tell, by anybody in academia or in any of the companies. At least they haven't published the stuff.
We haven't, people, Tobi, people, we have been working on that for a very long time. In fact, our event-based,
on DVS.
Wait, has dynamic storage to actually be able to control every pixel.
Yeah, but I'm talking about these particular cameras here that are in production, right? These DVS.
Okay, well, yeah, there is algorithms.
I don't think anybody's taking it on, but
right?
You know, it's a kind of a cool low-hanging fruit, right? I wish somebody would do it because it would make all the cameras much more usable. But I agree, it's right now, the words of wisdom are that learn what these parameters mean. I mean, not the details, you don't have to learn it, but a good software will expose these parameters in kind of a user-friendly way. Play around with those parameters because they definitely need to be optimized for particular scenarios.
So Tobi, this is a problem that biology also has to deal with.
Exactly. Yeah.
And as you know, there's adaptation all over the place at every level, and so you know, it's a solvable problem.
I mean, just talk about pupil control, right? Pupil control,
right?
Focus control, vergence control, all this stuff. Yeah, biology is just like it's completely. You're not aware of this stuff happening at all, but it's so critical to performance.
Yeah, and just the fact that you can adjust the dynamic range over 10 orders of magnitude, right? I mean, that's pretty good. I don't know any camera that can do that.
And not only, but you can also adjust the parameters with a global constraint, and it works beautifully.
It's not. Yeah, the problem is with this. The difficulty is a little bit that you don't have it's a multi-objective function.
Yes.
And it's not like automatic exposure control where you kind of want to get most of the pixels in the middle of the exposure. It's not quite clear what the objective is here, right? Because even to measure the signal to noise ratio it's not obvious how to do that. It's not clear what it means to get things in range for a DVS. You can increase the bandwidth here, but that increases the noise. You can increase the event threshold, that reduces the amount of events coming out, but it also gets rid of contrast you care about. You can increase the refractory period, but that means that it won't see edges close by.
You can set an algorithm and an objective function, and that can be done automatically. It has been done. I wish I could show the results now, but maybe soon.
That's a multi-objective function somehow.
Yes, it's a multi-objective function.
Right? But is it safe to say in general that part of the art of current supervised learning is the crafting of the loss function? In fact, the real skill is the crafting of a loss function.
It's a loss function, exactly. You need to come up with the right loss function. It took a while to actually come up with a class of loss function that actually work.
I can show you someone to
send me an email later. I will show you some pictures.
I think we should conclude.
Terry Stewart, as a challenge to the reinforcement learning group, I can't think of a lot better challenges to tackle than can you twiddle the bias settings and
that would be fun.
Remember, we did that. We attempted to do that, Guido, in Capocaccia. We attempted to collect data and attempted to automatically tune this parameter. I mean, for sure, it's not some trivial thing. Yeah. Somebody has to think hard about it and do some real experiments.
Do you have any results from when you tried it before that we could continue from, or?
I mean, I have a software class that's in Jair, right, that does the parameter control, but nothing's published. Yeah.
I can give you hints.
Tobi.
Cool. I will add that onto the list if people would like to play with that. Yeah.
Yeah, just saying it's non-differentiable, but there's a loss function that you could generate there that would make a great reward signal.
Okay, enough for today, I think.
I do have a camera or two around, so.
Oh, that is. By the way, that is your Conrad's original embedded eDVS. Basically, it has a DVS 128 by 128 pixel DVS that Patrick and I designed, where we taught Christoph Posch the art of this DVS design. Mm-hmm. He did the schematic layout, the schematics for that chip, and then below it is the 32-bit fixed point microcontroller. And with that thing, you could do all kinds of cool stuff like the pencil balancer robot. And, basically you would just write an algorithm in fixed point microcontroller code. In fact, this thing doesn't even have a divider on it. It only has one multiplier. So you could do multiply and fixed point adds. And so if you wanted to do a divide, like you had to do one divide operation in this beautiful pencil balancing robot, you had to amortize the divide operation over many, many cycles of the loop. You had to split the divide up over 50 cycles of the loop. I mean, it's just cool stuff. I mean, I like that kind of stuff.
So Tobi, is a little hint from biology, which is that everywhere you look, transforms in the retina and centrally are all log, right? There are laws.
Or relative, somehow relative. Yeah.
Yeah, it's all relative. Delta I over I is the signal that you use.
I mean, it's in a certain way, you know, this DVS pixel, I mean, does a very trivial operation, right? Just computes it only outputs the delta log intensity events, brightness change events. It turns out to be useful, but there should be so much more to it than that.
Yeah.
Terry, by the way, do you remember when people were working on all this stuff from the retina, like contrast gain control? People were looking for evidence that there was control for the contrast gain of the retina, which wasn't very clear. I remember from the early papers from, you know, the retina people, the retina biology people, they found fragmentary evidence that the retina would control its own gain for the contrast. In other words, if you showed it high contrast stuff in a large area, then the contrast gain of the retina would actually get turned down. But always that modulation seemed to be rather weak, right? It kind of, but you have to think that something like that is happening throughout retina and cortex.
Right. Yep.
It's kind of this hidden, you know, like Carver says, this 9/10 of the iceberg that you
the other
take for granted.
To keep in mind is that you can send up more than one signal. I mean, in addition to the differences, you know, with the ganglion cells on, off, surround. There are also some ganglion cells that send up the intensity. You know,
and much more complex things.
Yeah,
nobody really
you have many channels going up in parallel. You know, dozens.
Dozens, yeah. Okay, enough for today. We're already going almost 3.5 hours. It's enough.
It was a great session. You guys did a terrific job. Thank you.
Yeah,
thanks.
It's great to have so many people still stay around.